Hey, good morning there, ladies and gentlemen. Let's talk about this last week of geometry and make sure you guys are knowing all the things you guys have to know to be fully prepared for what's going to be going on in the future. So the way I approach this video is that if you indeed look at this video and say, well, I knew all that stuff, I would say you're probably in pretty good shape. Now, if you're watching this video and you're saying, wow, did we even talk about that in class? I would say you're probably pretty far behind and need to start thinking about how you're going to do some catch up that might be coming in before after school to talk to me, that might be making sure that you're doing all your homeworks and you're reviewing your notes and you're getting the notes. I don't know what that actually might be, but this is simply like a temperature check to see where you guys are in my class right now. Okay, so how did we get to this point in geometry? Well, you guys did a lot of work, and I'm going to speak specifically about transformations in vetting out kind of what you have to know about transformations to approach this current week in geometry. So here's what you guys have done. So let's say you have this thing called translation, which is just like a slide. You can describe that as like a slide very simply. You also have this thing called a rotation, and then you have this transformation called a reflection. Okay. Now, all three of these things have a layer which you kind of have to assume is true. Okay? I've been saying this is kind of like your initial conditions, but in the end, if you have a translation, you kind of have to assume that the lines connecting the pre-image to the image are parallel. In other words, you have parallel vectors. Okay? In a rotation, you have to assume that the pre-image and the pre-image have the same distance. Same center, and the same angle. If those things aren't true, then you simply don't have a rotation. For reflection, you have to assume that you have a perpendicular bisector that connects the pre-image to the image. In fact, that's kind of the theme throughout all three of these assumptions, if you will, is that these always refer to the pre-image image connection. Okay? Assuming that you have these things to be true, you can now move down a layer where you have to actually describe. Okay? And we've been talking about this as more as this is what you have to construct for your description. So if you have a translation, you're actually going to have to construct the vectors, or in the case where you actually realize, well, these vectors do have a certain length, you can also just call these segments. For rotation, you're actually going to have to construct to show the center and the angle. And then for reflection, you're going to actually have to construct the line of reflection. So in other words, you don't have to construct everything because you are assuming a lot of these things to be true. So in other words, like if in this layer, if the distance of these vectors if they're not the same, then you don't have a translation period. If they're not parallel, you don't have a translation period. For rotation, if these conditions on the assumption layer aren't met, these initial conditions, and then you don't even have to describe the rotation because there isn't one. If you don't have a line of reflection that is a perpendicular bisector for the reflections, then you don't have to go about describing the line of reflection because, well, you don't have a reflection to begin with. So here's kind of what I mean by that. If I have and let's call this example. Okay, so if I just have like this figure, and I have this other figure here. Okay, if these vectors that I draw from pre-image to image aren't parallel and the same length, then I don't have a transformation anyway, and I don't actually have to show anything. And you can see this is kind of what we call a non-example. But if we do have these vectors that are the same length, then I'll go to a triangle to make the drawing a little bit more simple. So let's put that right here. Okay, so if I do have these vectors that are the same length and parallel, I do have a transformation. Same thing for the rotation. Like if I don't have the same distance, same center, same angle, I don't have a rotation anyway. So I have to assume those things are actually present to even say, well, now I need to map it out. So again, let's go to a triangle example. Okay. So let's say my center of rotation is like here. Okay. I should be able to map out Oh, those just kind of got wild, didn't they? Okay. I should be able to map out this rotation by connecting the same center, and then these should be the same distance. I know it's not perfect, but again, I'm just kind of do a quick sketch here. Okay. So it's all those angles are the same, and each of the sets of lines are the same distance. I know blue looks a little off. Just go with it. Okay. I know that I actually do have a rotation. Same thing for reflection. I have to assume at some level that I do have a line that serves as a perpendicular bisector to each one. Therefore, I don't necessarily have to show it, but I can actually map out now this reflection. Okay, so that's what I mean. So that's how we got to this point. So now moving forward, now I can actually take these two shapes and actually identify pretty clearly what's going on. So like this has been the work of this week, getting to the point where you realize what I have to show to justify each of the following transformations. So we can actually just kind of pick some out of the hat here. This is a sheet I had you guys do. I'm not going to map them all out, but maybe I'll just map out a few just to kind of make sure we have the right flavor. So take this guy for example. So first I should notice a couple things. I'm going from ABC to DEF. So the order ABC goes A, B to C. So I should test that order out on my my potential image. This one goes DEF, DEF. So the order seems the same. They seem pretty much in the same orientation, just moved. So I'm pretty confident that what I'm looking at here is a translation. Okay. So that activates translation. Boom. Okay, so that activates some thinking for me. If I split it down, or I'm sorry, flip back down here to my little notes I made before, I have to show parallel vectors. In other words, parallel segments that are the same length. So I can do that. So if I definitely think that this guy is a translation, I do think it is. Where'd it go? There it is. The first thing I need to do is kind of map out some segments that connect the preimage to the image. Now, do keep in mind the order matters. So A is going to connect to D, B is going to connect to E, and then C is going to connect to F. So that's what I should be looking at for my vectors as well. Okay, so let's check that out. So A connects to D. We'll get purple. B to E. And then C to F. Now, if this is indeed a transformation, these vectors should actually be the same. And I can kind of do a quick visual check. That seems to me like precisely anywhere on the shape, those vectors are all the same. And since they're exactly the same, like precisely the same, I can also claim that they are parallel, which I'll mark by chevron. And of course, they just tested the same length, which I'll indicate by a tick mark. Okay, so how do I describe this? Well, I have to note the important information, and again, the important information in this case happens to be like how the pre-image moved into the image. In this case, vectors. So I can definitely say, in terms of my description, that we're translating. So give us a target, in this case, ABC, to the target target image, DEF, through the important information, the vector. And I used to pick one of these vectors. It doesn't really matter which one. I'll just pick the first one, AD, and then that's how we're going to mark that vector. Now we can also summarize that information using a rule, and that's just kind of a shortcut to those words. So I have this transformation along AD of triangle ABC, which will take me to triangle DEF. Okay. The rule, as you guys kind of notice, is just a summary of what was actually going on in the verbal description. It's just a more concise, more mathematical way to write it, if you will. So that's a transformation. Well, let's pick a rotation. This guy. I like this guy. It's my favorite guy. So one again, I do notice I do have a transfer or a rotation here, and the difference is because it's not just been flipped, it's not been slid, it's actually just been turned. So in terms of identifying the important information, I have to assume the same distance from A to C, or A to the, excuse me, let me reword that. I have to assume the same distance from the pre-image to my center and the center out to my image, along with the same angle. So I just have to kind of map those two things out. So if I look at this angle formed between A, the center C, and then A prime also to that center. And again, I'm assuming that's the center because that's the one piece that has not moved. I have to examine that angle, and the actually angle has to be the same for all three of them, or two in this case, excuse me. So B to the center out to B prime, that has to be some sort of angle as well. Now, again, we have to kind of confirm that these are the same thing Well, I don't know if that's going to work. Let me try it one more time. Oh yeah, there we go. Okay, so if I kind of take this angle and I turn it, I can confirm that those are indeed the same angle. Okay. Now, some people I saw drawing circles on top of this. It's not a terrible idea to do that because they do have to be the same length. But I would also claim that if they're not the same length, this isn't a rotation anyway. So another way of saying that is if you want to go ahead and kind of sketch out that these are both on the circumference of a circle, I say go ahead. I don't know if it's necessarily necessary though, because that just has to be one of those assumptions we have to make. Now, in terms of the description, we are dealing with a rotation here. So I would say a rotation of triangle ABC about center C, okay, or C prime. Actually, they both work. By angle. Now here's where it kind of gets messy. Now the angle you can name a couple different ways. You can simply give it a letter, like call this like angle X degrees if you want, which is okay, but I don't think we need to do that. Remember, we do have a 3-letter naming convention for angles. So if I go from A to C to A prime, I can actually just use that as the angle. So by angle A prime, and give it a image, A prime, B prime, C prime. So again, we're incorporating not just a diagram that's been augmented, but a description, and then of course we can do a rule as well. Big R for rotation about center C using angle AC A prime of the target, or sorry, the pre-image ABC to the target image A prime, B prime, C prime. So again, you kind of see how what we're really kind of doing here is simply describing the rotation in terms of what you have, what you're doing to it, and going to where the final destination is. So let's get one more in. Let's get a rotation. Let's talk about this guy. Or, I'm sorry, a reflection. Let's talk about this guy right here. Okay. So not been twisted, not been slid, but actually been flipped. So the important information we have to identify, if I can go back and reference my notes again. Okay. The important thing we have to identify is a line of reflection. Again, we have to kind of assume it's a perpendicular bisector. If not, then we don't have a reflection anyway. But what I really want to map out is that line of reflection. So my thought is the line of reflection will be right here. Okay. Now if we want to confirm or show perpendicularity with a bisector, we can confirm that these distances are the same, and that's 90-degree angle. Now we don't have to show the other ones because they're actually on the line of reflection and they're not even moving. So we do have a reflection here, so let's go ahead and map this guy out. So reflection of triangle ABC. Over. Now we have to identify this line, but luckily the points are already there. Like I have points that are on the line, so I can definitely just use, say, like AB. We could also use DE if we like, to triangle DEF. Okay, so if we want to go ahead and rule this guy, we have a reflection over DE of triangle ABC to triangle DEF. Okay, so this is where you need to get for this week. So the whole point of this week is to be able to talk about, describe really well these transformations. So think about the distance you guys have covered intellectually in describing these things. You used to talk about that simply as a slide, which isn't a bad way to say it. I would just say it's a holistically casual way, a holistically elementary way, or oh, what's the term I'm thinking of? And I'm at a loss. Like casual, it's like a non-specific, non-studious, if you will. But now you guys are able to describe it actually much better. You know you need to talk about vectors that are the same distance, and that's kind of what it looks like. In the same way, you used to talk about rotation simply as a turning. In fact, I asked you guys to brainstorm words on how to describe rotation, and everyone said, well, it just spins or it turns or just kind of stays in one place and then moves in a circle. But now you guys know so much more. You have to talk about distance, center, and angle, and you have to be able to diagram the distance, center, and angle. And the same for reflection, like you can totally talk about it just as a flipped or flipping. But now you guys know you have to show so much more, a perpendicular bisector or line of reflection. So that's where you guys are now. Where you're going to take this, though, is somewhere completely different. Now we're going to take this and actually use it as an offensive tool to create a mapping. So up to this point, and we're going to practice even at the beginning of the week here, is going to be how do I still describe something that's been changed by rotation, reflection, translation, or actually combination thereof. But where we're going to be going by the end of the week is I'm going to give you a triangle. I'm going to say, hey, what happens if you do these things to it? Um, what does that end figure look like? Can you still claim that it was a mapping? Okay. So anyway, that's going to be a target more for this week. Next week, this was this week. That's what I got. Thank you guys for listening. Don't if you need to comment or post a question, let me know.